Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk to you about this notion of descent data, which vastly generalizes the notion of transition functions that you see to construct vector bundles. And in so doing, not only do we generalize this notion of transition functions to the setting of Grothendieck topologies, but we can also construct other more interesting objects known generally as twisted forms. Okay, so to set the stage here, let's just recall what happens when we try to construct vector bundles using transition functions. Okay, so what's the data that's used? Okay, so I want to just set your mind and give the situation of what's going on. So here X will be some topological space. And remember, that gives us a Grothendieck topology. So what's involved with the Grothendieck topology is you have some category. In this case, it's just going to be the category of open subsets of X, where the morphisms are just inclusions. And then you have the notion of a covering. So it's various collections of morphisms which cover in this case. Okay, so if you want to build some sort of a vector bundle on this X, okay, you start with a finite dimensional vector space V, and that's basically going to give you the fibers of X, the vector bundle on X at every point. So this will have some fixed dimension, okay, and let's make that dimension R, so that's the rank of the vector bundle that you're looking at. So what happens when you talk about transition functions is basically you want to glue copies of this vector space to itself on different patches of your open cover. Okay, so to glue V to itself, you need some sort of automorphism of that vector space. So we look at aut V, which is just the general linear group on V. And importantly, we'll introduce here the aut sheaf, aut underline V. So what's that? So aut V just means that for any open set U here, okay, you just look at the continuous map U to the automorphisms of V. So remember, if you want to look at transition functions, okay, so if you want to go from one patch to another patch, what you do is so you look at the intersection, okay, and for each point of that intersection, you need to have an element of GLV, and you want this element of GLV to vary nicely, so continuously, so it has to be a continuous map from U to aut V, okay, so that's where the data of a transition function lies. Okay, so let's go to the general setup and see what's going on. So here we have some arbitrary Grothendieck topology, and suppose we look at some covering of, say, some X here. So UI to X can be a set of UIs to X. So the next thing that you want to do, remember, is you want to look at the analogs of things like the intersections of those UIs. And one of the points of looking at the Grothendieck topology is that this notion of intersection can be nicely generalized by looking at fiber products. So in this Grothendieck topology, there's the assumption that you can take these fiber products. Okay, so for example, the analog of UI intersect UJ, I'll denote it by U subscript IJ, is going to be UI fiber product over X with UJ. Okay. And the other thing that you can do is once you have this fiber product, you can project onto the factors UI and to UJ. So this will be the first projection onto UI and the second projection onto UJ. And the idea here is that if you have an object on UI, if you pull back along this projection 1, that's like the restriction onto this UIJ. We'll also need to look at the triple fiber product UIJK, which is UI crossover X, UJ crossover X, UK. And now you can project onto various combinations of factors here. You can project onto the first two, UI cross UJ, that's UIJ, and that's projection 1, 2. You can project onto the outside factors, UIK via projection 1, 3. And you can also project onto the last two via projection 2, 3 to UJK. You can also project onto each of these individually. For example, if you project onto a UK, that's projection 3, which you can also get by projecting firstly onto the last two, and then onto the second of those ones. And I guess you can also project onto the first and the last one, and then the last one. So there are various ways you can go around, okay? So that's what you have. Okay, so I want to introduce now the idea of a descent data. So I won't present a proper definition, but what I'll present here will be enough to give you an idea of what's going on and this all-important concept. Okay, so what you want to do is you want to consider VI to be objects on these open patches, so to speak, these UIs. Okay, so the examples to keep in mind here are, firstly, if you're looking at vector bundles, maybe these UIs is where you trivialize a vector bundle, in which case VI, you can trivialize that object and it becomes just UI cross CR. Okay, so more generally what you can do is you can replace this CR with other types of objects. For example, you can replace it with just the algebra, the complex algebra of R by I matrices over C. Okay, so VI could be UI cross MRC. You can have more complicated things as well. Instead of this example here, if we don't assume that the UIs trivialize your vector bundle, okay, you can just have these objects VI to be just vector bundles of some fixed rank. And this will also work in that instance too. Okay, so what is descent data consist of? Okay, so what you want to do here is you want to consider this set of objects. Okay, so you'll have some Vj on here, and you're going to pull it back up to Ui cross Uj, so this Uij, that's by projection 2 star. So we're going to assume that these objects you can pull back. Okay, that's part of what's involved in this theory. Okay, so we assume that you can pull it back, and then you're going to pull back Vi, which is on here, up to this Uij. So these are now objects on Uij, this fiber product. Okay, and you want some isomorphism up on this Uij. Okay, so you want to do this for all pairs of Ij's in this cover. Okay, so just to see what's going on here. Okay, so this is basically the data that you give for transition functions. So let me explain that in this example here. Okay, so in this example, suppose you have trivialized some vector bundles. So this Vi, you can assume to be UI cross CR on this patch UI. Okay, then what happens when you firstly, let's look on Uj. Okay, so you look at Uj, this is the Vj here, will be Uj cross CR, and you pull it back. So basically that means that you restrict this UI cross CR to the intersection of UI intersect Uj. So that's Uij cross CR. That's the pullback of this Vj to here. And similarly, you're going to pull back this UI cross CR, okay, to the intersection. So that's Uij cross CR. And you would want some isomorphism of vector bundles here. So that means over each point of Uij, you want an automorphism of CR. And of course, that should vary smoothly. So that's basically your transition function, this eta ij, which is an element of this sheaf, or rather, it's a section of this sheaf over this Uij. Okay, so this is a very natural generalization. Okay, so this type of data is a natural generalization of the data that you give when you give a transition function. But now this applies to any Grothendieck topology, okay, as long as you can talk about things like pullbacks of these objects, okay? And of course, you have this setup of a Grothendieck topology. Now, so that's the data that's involved, but you need some axioms on this data. And the axiom that is required here is basically what's called the co-cycle condition, or more precisely, the one co-cycle condition. So let me just go through that. So this is rather interesting how this works. Okay, so it looks a bit complicated, but basically for any triple product like this, I want this diagram to commute, and it's going to be a commutative diagram up on the triple product here. Okay, so let's just see what's going on. Okay, so let's look at this first map, theta jk. Okay, so that's basically looking at what happens when you go from the pullback on vk up to the pullback on vj. Okay, so this theta jk goes from projection 2 upper star vk up to projection 1 upper star vj. And I'm going to pull that back by projection 2, 3. So I go from projection 2, 3 upper star, projection 2 upper star vk to projection 2, 3 upper star of projection 1 upper star vj. So we take this in the case where you have vk and vj, and we pull it back by this projection 2, 3. Okay, and you'll get this map from here to here. Okay, so let's simplify what this is. So here, if you do projection 2, 3 first, and then projection 2, that's this combination here, okay? At the end of the day, you just project it onto the third factor. So this is just projection 3 star, projection 3 upper star of VK. And here, what's this? Well, if you work out similarly what this is, of course, you've just pulled back Vj via projection 1. So Vj will go from Uj to Ujk. That's the first projection. And then you pull back via here to the triple product. So you're just projecting onto the second factor. So there's projection 2 upper star Vj. Okay. So essentially what this first map does is it takes the object on the UK, last one, and it pulls it back to the triple product. And there's an isomorphism of that to what happens with the object on Uj, the middle factor, and you pull it back to this triple product. Okay. And similarly, you can do the same thing now with theta ij. You've got an isomorphism from basically the object on Uj, that's Vj, to Ui, okay? The object on Ui, so that's Vi, okay? And that's what this projection 1 to upper star of theta ij is, okay? So that goes from, and the key point is that you see you can rewrite this projection 2, 3 upper star of projection 1 upper star Vj as projection 1 to upper star of projection 2 upper star Vj. So that's a good exercise to see, and it uses the same reasoning as we saw here. And this will map to, of course, well, theta ij goes from projection 2 upper star Vj to projection 1 upper star Vi. So we can pull that back by projection 1, 2 upper star to get this map from here to here. And again, this, if you work it out, is just projection 1 upper star Vi. And if you think about what all these objects are, okay, this one here, well, you can also do the last possibility, which is instead of using projection 2, 3 upper star and projection 1, 2 upper star, projecting onto the first and the last, so you can also project onto the first and the last, that's projection 1, 3 upper star, and pull back theta ik from there, and that will go from projection 3 upper star Vk to projection 1 upper star Vi. Okay, so these are all objects, okay, up on the triple product, and we have maps between them that you get from taking these descent data. These, well, there'll be 3 of them, okay, that you pull back accordingly so that they're all living up on Uijk. And these 3 isomorphisms have to form this commutative diagram like that. Okay, so it looks a little bit complicated here, but what I want to show you now is that actually this is a very, very natural generalization of the usual co-cycle condition that you see for transition functions when you want to build a vector bundle. Okay, so let's just see how that works. So let's have a look at this first bit here. So remember, what is this theta jk? So remember, this is basically the usual transition function, which tells you, okay, suppose you have 3 open sets like this, ui, uj, and uk. Okay, so the theta jk just is telling you the patch that's on UK, how do I glue it onto the patch that's on UJ? Okay, that's what you want to do here. That's that eta jk. And of course, this only takes place on the intersection of UK with UJ. So what does the projection 2, 3 upper star do? Remember, you pull it back up to the triple product. So the triple product here is a triple intersection. So you're now really looking at the triple intersection here. Okay, so you have that gluing, which was initially on the intersection of UK with UJ, now you restrict it to this bit here. So suppose you do that gluing, and then you compose by doing the gluing from UJ to UI. Of course, you've got to restrict that to the triple intersection here. Okay, that has to be compatible if you want to glue straight from UK to UI, which is the eta ik uijk. So these 2 composites are basically just what you get in the upper row here. That's theta jk is your eta jk, and you restrict it by the projection 2, 3 upper star. This is eta ij is your theta ij, and you restrict it by the projection 1, 2 upper star. And then the theta ik is your eta ik, and you restrict it by the projection 1, 3 upper star. So now we see here that we've completely generalized the notion of a transition function by this notion of a descent data, and it works for Grothendieck topologies. Okay. So the next thing to see is that, well, we said here that this Vi could be any object, okay? So let's look at more general types of objects and see what we can do, okay? So the basic idea and the viewpoint that was proposed by Grothendieck, is this notion of a twisted form. Okay, so what's a idea of a vector bundle? So the vector bundle he wants to think of as a twisted form of x cross CR. Okay, so what's meant by a twisted form? So if you have this object x and you basically want to have this fixed vector space CR at every single point, you can do that. A twisted form, that means that firstly, locally, it's going to look like that. So it'll look like that on some cover. So on each UI, you'll have that. But what we're going to do is we're going to twist that because once we have this local description, okay, where they all say UI cross CR, we're going to glue them back in different ways. So we'll twist the gluing. So much as when you construct the Mobius band, okay, you can basically cut it, which corresponds to undoing, to trivializing the vector bundle, and then you glue it back together, but not in the usual way, in some twisted way. So it's a twisted form like that. And this way you put it back is via the transition functions. Okay, so that here now I've generalized to this notion of a descent data, theta ij. And the only thing is that to note here is that, okay, so you certainly can construct it that way, but how do you know when two vector bundles are the same? So the key point here is that, well, the only thing that you can do is that you can change the way you trivialize the vector bundle. So the way you write this VI as UI cross CR. Okay, so the way you can change this is, well, at each point of UI, you can give some sort of automorphism of CR. So that's really some section of the sheaf aut V over UI. So you can change the trivialization on each patch. So you can change it by, what you do is you give basically a one co-boundary. So it's given by the data of a choice phi I of a section over UI of this aut CR. Okay, and that will allow you to change the descent data in a fairly obvious way that I won't go through here, but the basic idea is that, well, since you're talking about essentially one cocycles, okay, so you want descent data, these things, which satisfy this cocycle condition, so that gives you the notion of a one cocycle, and you can multiply them by these objects here, so basically up to one co-boundary, so that gives you an object of, and this is something that you can define, the one cohomology, okay, H1. So let's try to apply this to different objects. Now let's suppose instead of looking at x cross CR, you look at x cross this matrix algebra of R bar R matrices over the complex numbers. Okay, then you'll get the notion of what's called a twisted form of this x cross MRC, and that's a very, very important notion in mathematics known as an Azumaya algebra. And this arises in lots of different contexts, and in particular, you can even look at it in the context of number theory, okay? That's quite important there, and also in the theory of central simple algebras. Okay, so that's something that we'll have to look at a bit more later. And what's really nice is that if you want to study these, well, you can study these in exactly the same way as you want to try to study vector bundles. So you can try this approach of using transition functions. So here we look at descent data again, okay? And the only difference here is that, well, when you glue the MRCs, these matrix algebras to themselves, you need automorphisms of this matrix algebra, okay? So that's the only difference, is that in this whole theory, you just replace, instead of the sheaf of automorphisms of now what was before a vector space of rank or dimension R, you replace that with automorphisms of this algebra, this matrix algebra. And it turns out, actually, it's a lovely theorem, the Skolem-Noether theorem, that if you want to have any automorphism of this matrix algebra, it comes from conjugation by some fixed matrix. And since all the scalar matrices, when you conjugate by a scalar matrix, of course, it's the identity. And in fact, that's the only thing that gives you the identity automorphism here. What you're essentially doing is looking at this automorphism group, which is just the quotient of GLR by the scalars, or PGLRC. Okay, and that gives you this example of twisted form. So these twisted forms you can also do in other settings. I've just presented this rather interesting one here for concreteness, but it shows you the power of this technique. I hope you enjoyed this adventure in pure mathematics.